These notes are set up in a Cornell notes form. I don't know if any of you have used any of those in your other classes, but it's supposed to allow to give you room over here to write topics or important things, and then you fill in the information here, and at the end you're supposed to be able to summarize what you've learned. If you'd like a copy of this paper to follow along with, you can get to it from my website and then print it out and follow along. If you want to write this on your own paper, that is also fine. Okay, today we're learning about exponential functions, which is a function where the variable is in the exponent. Let's figure out what these look like. You might have heard of exponential functions when you're dealing with things like population growth or depreciation, like depreciation of a car value, or maybe radioactive decay. Those are some common uses of exponential functions. Okay, let's go ahead and just graph these by creating a table of values. So I'm going to pick any numbers for x that I want to pick. So let's do some positives, some negatives, and of course 0, and just plug them in. 2 to the negative 1 power. Well, anytime we have something to a negative power, we flip it over. So that makes it so that we have 1 over 2 to the first power. The answer we therefore get for y, in this case, would be 1/2. Next one, 0, 2 to the 0 power. I don't know if you remember your exponential rules, but the rules of exponents say that anything to the 0 power is 1. So the answer is 1. 2 to the first power is 2. 2 to the second power is 4. We could keep going with positives and negatives. If we went with further negatives, we would get smaller and smaller fractions. If we go with larger positives, we will get bigger and bigger numbers really quickly because it's an exponential. So the numbers are going to keep, in this case, doubling in value. Let's go ahead and plot these points. So negative 1 up 1/2, 0, 1, 1, 2, and 2, 4. These 2 points right here are very key points. This one we're going to talk about later. Every exponential function has that point at 0, 1 because anything to a 0 power is 1, unless the graph has been transformed, and we'll talk more about that in a few minutes. This other key point has to do with our base of our exponent 2. 2 is the base of the exponent, so that means when we plug in a 1, the base to the first power, the answer we get is that base. So whatever your base is, in this case the base is 2, that's the number that when we go over 1, we go up that base number, and that kind of shows us how steep our graph is going to go. Okay, now no matter what numbers we plug in, the smaller and smaller negatives we put in here, the smaller and smaller fractions we're going to get. But we are never ever going to get 0 from an exponential. So therefore, just like we learned in our last section in our last chapter about rational functions that have asymptotes, exponential functions also have asymptotes where the graph is going to get closer and closer to 0 but never quite get there. Okay? Our second problem we're going to do here, notice the base has changed. So this one had a base of 2, this one is a base of 5. What do you predict is going to change about our graph if we have a base of 5 instead of a base of 2? If you remember what I said earlier about that point, you might be able to guess what's going to happen. Let's go ahead and plug in some numbers and see. So if we plug in a negative 1, this time we get a 1/5. Plug in 0, we always get 1. Plug in 1, we get 5, and plug in 2, we get 5 to the second power, which is 25. Look how big it got really quickly. So now let's graph these points and see what the difference is. Negative 1, 1/5, 0, 1, 1, 5, and then of course the next one's off the graph. So what do you notice about our exponential function? Because the base has changed, well, it's steeper. The growth is happening a lot faster. So this would be a population that grows really quickly. Okay, now let's deal with bases that are fractions instead. What do you think is going to happen if our base is a fraction? Let's plug some numbers in and find out. Should we go with our same numbers? Well, we can. We might end up finding out that we'd rather done a little bit different numbers, but we can do the same ones and see what happens. Negative 1, 0, 1, and 2. So 1/2 to the negative 1 power flips that fraction over, so it becomes 2. Just like on this problem, when we did 2 to the negative 1, it became 1/2. So this is just the opposite, the reciprocal of that. 0, 1/2 to the 0 power doesn't matter what to the 0 power, it's always 1. And then 1/2 to the first power gives us a 1/2, and 1/2 to the second power means we're taking 1/2 squared. So 1/2 times 1/2 is actually 1/4. It's a smaller fraction. Let's go ahead and graph these points. So at negative 1 we're up at 2, at 0 we're at 1, at 1 we're at 1/2, at 2 we're at 1/4. Do you see what's happening and why we might have wanted to put more points in over here to see better what this is doing? If we use our first problem as an example, we would know that if we plug in a negative 2, it's going to go up to 4 because it's going to flip our number over and square it. So that just gives us another additional point up there if you'd like it. We still have our asymptotes on the last two problems. We still have our asymptote at 0, where our exponential is never going to go below 0 and be negative. So look at our domains, all real numbers from left to right, all real numbers, left to right, all real numbers, but the range is starting at 0 and upward. And so it doesn't include 0, but starts above 0. Never reaches 0. What do you think is going to happen if our fraction's a little bit smaller? Well, what happened when we had a larger base here? You can probably guess that a smaller fractional base is actually going to make the depreciation steeper. Okay, so let's go ahead and plug in some numbers. 0, negative 1, 1, 2. So 1/4 to the negative 1 power is 4. Notice how the answer is not negative 4. Don't do that. So 1/4 to the negative 1 does not make the 1/4 negative. It simply flips that fraction over to be a positive 4. 1/4 to the 0 power is 1. 1/4 to the 1 is 1/4. 1/4 to the 2 is 1/16. That's really hard to graph, especially with my fat Sharpie marker here. Anyway, I go left 1, up 4, 0, 1, 1, 1/4, 2, 1/16, and of course it did as I predicted and gave me a little bit steeper exponential depreciation graph. Okay, what do you notice about example 1 and 2 compared to examples 3 and 4? Well, these are going upward. They're what we call growth, exponential growth. These two are going downward. They're what we call exponential decay. Alright, so 1 and 2 are increasing, and 3 and 4, of course, are decreasing. So that's kind of what I had in mind you would write here. I don't know if I want to take the time to write it. I guess we could write 1 and 2 are, let's just write it increasing. 3 and 4 are decreasing. So does it have something to do with the base? Well, it must. Notice how the bases for the increasing ones are numbers that are greater than 1, and the numbers for the bases that are decreasing are between 0 and 1. So for f of x equals a to the x, an exponential function with base a, the function is increasing. Maybe I didn't leave enough room on my paper here. Increases if the absolute value of a is greater than 1. So if this number here in front is bigger than 1, right? Or decreasing if our absolute value of a is between 0 and 1. And the reason I say absolute value is because it could possibly be a negative, which of course if we've learned from transformations in the past, it's going to flip that upside down. So instead of all of our y values being positive, all of the y values will be negative. The negative in front will just take all of these answers and make them negative instead, thus flipping the entire graph over. Okay, let's look at some basic general characteristics of our exponential functions. Some of these we've already talked about based on our graphs. Domain, of course, is negative infinity to positive infinity. Range, 0 to infinity, because of that asymptote, right? X-intercept, none. Why is there no x-intercept? Well, it doesn't cross the x-axis because there's an asymptote there. Y-intercept, we talked about this because anything to the 0 power is 1. There's always going to be an intercept at 0, 1, unless we transform the graph, which we'll talk about in a minute. And then the horizontal asymptote will generally be at y equals 0, unless, again, the graph is transformed. So here we have our basic transformation issues here. A number out front is going to stretch our graph. For example, this one's a lot steeper, skinnier than this one is because it has a bigger number for A, which is 5, instead of a smaller number for A, like 2. So A is our stretch, and then H would be a horizontal move. The horizontal moves are a little bit tricky to see. In order to do a horizontal move, you probably just want to remember that point at 0, 1 and move that point horizontally, the H value, and notice that that H value is part of the exponent. And then the K value would be moving it up and down. So if we were to add a number on the outside, that's just going to take our asymptote that's normally at 0 and move it up or down. And of course, like we just said, our graph could also reflect if it had a negative there. So if you want, I can go through and explain each detail. So these are things we've already learned before. Let's write this one down. I didn't write that one. Negative x would reflect over the y-axis. Now that's kind of interesting. Let's stop and talk about this one. Remember how x is the exponent? So if you take the exponent and you make it negative, doesn't a negative exponent mean you're flipping that number over? So putting a negative x here basically means we're turning it into this problem, doesn't it? 2 to the x power is the same thing as 1/2. 2 to the negative x would be the same thing as 1/2 to the positive x. So if we started out with this one that has a base of 2, doing 2 to the negative x technically changes our base to a 1/2 because the negative x flips it over, which means our graph is going this direction instead. So there's two different ways to create your decay graph. It can be done either by putting a negative in the exponent when you have a number that's larger than 1 here, or it can be done by leaving the x positive but changing this to a fraction. Either one has the same result of reflecting it over the y-axis. Okay, negative x reflects over the y-axis. Of course, negative a would reflect over the x-axis upside down, like we would expect. H, so A is the stretch, so that there's a point at 1, A. Remember how we talked about that at the beginning, where this was a 2, because we do 2 to the first power, so 2 to the first power is 2. So you go over 1 up 2. So whatever your base is, that's the number over 1 up 5. Over 1 up 1/2. Over 1 up 1/4. Whatever that base is, you go over 1 and up that base. Okay, so stretch point, the A causes the stretch. For example, there would be a point at 1A. Okay, and then of course we have H, which means it's moving left or right. Move left or right, and it's the opposite direction. And then K would move up or down. Okay, I don't know if we've done enough transformations in the past that we don't necessarily need examples of this, but just in case, the next video is just going to be examples. So if you feel like you can do transformations without the examples, don't worry about it. If you're having a hard time with them, you can go back and watch some of these.